Today we're delighted to have Kevin Fu, who is an associate professor of EECS, Electrical and Computer Science, at the University of Michigan. Kevin has done groundbreaking work in the area of computer security and is really well known for his work on improving the security of medical devices. Security solutions resulting from his research that foresaw the risk of malicious software affecting hospitals and ransomware. He made these discoveries, decades before they were actually happening in the real world. In recognition of this, he's been serving as the inaugural acting director of the medical device cybersecurity at the US FDA Center for Devices and Radiological Health, and he's also the program director for cybersecurity at the Digital Health Center of Excellence. Kevin has been recognized as an IEEE Fellow, Sloan Research Fellow, and the MIT Technology Review TR35 Innovator of the Year. He received Best Paper awards in some of the best venues in computer security, such as Using Security, IEEE Security and Privacy, and ACM SIGCOMM. So without much further ado, let's welcome Kevin Fu.
Thank you so much, David. Let me share my presentation. Just a moment. All right, I think you should be able to see those slides now. Oh yeah, I can tell because I just saw the reflection off of all your faces. That was a test of the optical system, by the way. Okay, I got to do that in coding more often. So hello, let me just be clear. Thank you for the introduction. Today, I'm appearing before you as Professor Kevin Fu, representing myself from the University of Michigan. I am not at all wearing my FDA hat today. If you have questions for me related to the Food and Drug Administration, I'll have to put on a different hat, but that'll be for another discussion. So what I wanted to talk about today, and it's really exciting to be here with SRI because of the profound implication of computer security of semiconductor products on society, in particular medical products, ranging from medical devices to pharmaceutical factory floors. There's just a lot of interesting research to be done. And I'm going to be talking today more about research, I would say, that's classic basic research, where you're thinking 5 to 20 years out. These are not products per se, but these are about what do we need to be doing in academia to be in a place such that 10 years from now, we're not running around saying, oh my God, how did we get here if we had only done X? And so I'm going to talk today about some of the risks and some of the ways to mitigate risks with good security engineering for medical products. So just a little bit about my background. I'm talking to you today from Ann Arbor, Michigan, where I'm at the University of Michigan. And as I mentioned, I do have a role at the Food and Drug Administration. I'm not wearing that hat today. I'm also not wearing this shoe today, but I previously worked in health information technology. And as you can see there, I can prove I existed in the 1990s. Rolling out paperless medical record systems to every single patient-facing room in a community hospital. And that really led me into a lot of what I'm going to talk about today, because I noticed as you're caring for patients, the profound implications of technology on patient care, as well as on the clinicians. And I watched how security technology disrupted the workflow of the clinicians. If you're a security practitioner, you usually don't see this because you're not working in the field where you see your products in use. But if you work in a hospital, you'll see all sorts of interesting misuse of technology that I would attribute to the early design. So I'm going to talk about sort of two domains of research today and how they relate to each other. A little bit of medical device research, and here are a few of the papers that I'll be selecting from today. And then also classic embedded security research. And embedded security research is a very vibrant field today. It's sort of at the edge of hardware and software and semiconductors and cryptography, all sorts of exciting things happening in boundary conditions. And so we're primarily going to be talking about embedded security with implications to the medical world. And I'm not sure if that was a question, David, but I see you have a little green outline. I'm not sure if you're trying to raise my attention. Okay, good.
No, yeah.
Okay. Well, let me play a short video to sort of level set where I'm coming from. Before we start to talk about security issues, let's talk about reliability issues. And so here's a short video, I hope it's going to play, from the New York Times several years ago. And let me just play it and see what happens. David, maybe you can give me a thumbs up if you can hear it as I play. I don't know if you hear the audio.
I'm not getting any sound.
Where's that beeping noise?
I can hear it. Where's that beeping noise?
So this gentleman's oven, the broiler would spontaneously ignite whenever his cell phone rang. That was not part of the design requirements of this particular oven. And so when I saw this video of an oven turning on its gas ignition system when the guy's phone rang, I thought, that's an interesting security problem. Because if this is happening by accident, imagine what would be going on if an adversary deliberately tried to emit particular RF waves in order to cause these kinds of unwanted sort of thermal runaway. I was trying to track down this particular oven through eBay. I did not have any luck finding it, but I suspect that likely the cell phone was hitting the resonant frequency of a small piece of wire attached to one of the buttons on the oven that led to the microprocessor that would look for a particular voltage in order to indicate turn the broiler on. I guess we'll never be able to figure it out, but that's what I would put my money on. So with that in mind, I want to try to contrast traditional software, hardware engineering with security engineering. It's a very different world, a very different model. And I'd like to illustrate that with a photo I took in Puerto Rico at a hotel where they had a keypad on the wall. And I asked the question, I often ask the question to my students in security engineering classes, what does it mean for this keypad to be correct on a door? And they usually say, well, if you enter the correct pin, the door will open. And then I ask, how do you define security for this door? That's a lot harder because security is a negative goal, very similar to safety. And so usually I'll get a response such as, if you don't know the pin number, you won't be able to open the door. All very reasonable, natural notions of security, but completely wrong. Because in the real world, things are designed and built by committee. And in this particular case, the hotel decided to print a plastic placard of the actual code to get through the door. And if you can't read the English numbers, they have it in Spanish as well. So somebody clearly went really out of their way to make sure you could get through this secure door. This is a true illustration of how security usually works in the real world. It fails outside of your model of thinking. Usually the first reaction a vendor will get is, well, that's not fair. A bad guy's not allowed to do that. Well, guess what? The bad guy can do anything they want. And it's the defender's job to be creative enough in their threat modeling that they can predict these kinds of bizarre security failures. And this is where the human element comes in. So this meme's been floating around for decades, but it also sort of illustrates the problem of if you design it with the wrong threat model, people will be able to break through your snowy grasses of your parking lot gate. And that's probably a big problem in Toronto right now. So on the more serious side of how to sort of visualize what is computer security versus classic sort of safety engineering, you can think of it as, in the safety world, you often think about probability distributions of failure. They tend to have Gaussian bell curves. You might be able to use past performance to predict future performance. That's fairly reasonable when you're talking about defending against Mother Nature or a hurricane. When you're talking about security, you now have an intentional, dedicated adversary who's sentient. Most hurricanes aren't sentient, I hope. And so if the adversary knows that they can cause an unsafe condition just 1% of the time, they will do everything in their power to make that happen 100% of the time, essentially stacking the deck. So the world of cybersecurity really is not able to use notions of probability or likelihood in any reasonable manner, because the adversary can always make it to be whatever probability they want. So with that in mind, let's think back about a decade when I was, I began working on medical device security a couple decades ago, but about a decade ago, in the United States, we have an office. It's sort of the watchdog for the federal government, and they analyze all the agencies to determine shortfalls and gaps. And this particular office wrote a document saying FDA needs to expand its consideration of information security for certain types of medical devices, effectively. We had also done some early work showing how to induce sort of strange failure modes in implantable medical devices, in particular this defibrillator, by emitting certain RF patterns near the device. Also at that time, it was just beginning to see malware entering the hospital systems. Ransomware did not exist at the time, 10 years ago. It could have, but it was definitely not noticed. But it was a precursor for a lot of the ransomware we're seeing shutting down everything from hospitals to parts of the supply chain today. So on the medical front, let me give you sort of a 2-minute sort of residency, and you'll magically be able to have great cocktail parties about how medical devices work. So in 2006, I began working as a private citizen, going off to the FDA, urging them to please consider medical device security in their pre-market considerations for deciding whether to let a device enter the United States market, which today is about 140, 150 billion. Then in 2008, we published some work showing that we could exploit an implantable defibrillator to cause it to emit a shock that was life-threatening. A series of really bizarre sort of social things began to happen, including I've sort of lost count of the number of TV dramas that use some kind of security incident of a pacemaker as their plot line, but there definitely is a lot of hype around it, and I hope to demystify that a little bit today. So I guess this was 14 or 15 years ago. This is a screenshot of what my graduate students brought me after they had reverse engineered the radio communication between a pacemaker defibrillator and an external device called a programmer. A programmer is essentially, like a wireless control, basically, of the implant, typically using a proprietary RF technology. And so they had built their own decoding systems, and what they had found was basically there was what was effectively a complete electronic health record in the clear without any apparent cryptography protecting the information. This was concerning because to me, it was an indicator of, well, if they're missing cryptographic controls on this particular component of the device, then it's probably also missing from some of the more safety critical functions. So indeed, our second set of experiments had to do more with the safety of the medical device. And a few MIT students had replicated this experiment some time ago. And we discovered that if you record the command to, first of all, disable all electrical therapies, you can kind of think of it as like a tape recorder for radio. And then you replay that later after, you replay that later. And then you also replay the radio command to do what's called a command shock. A command shock traditionally induces something called ventricular fibrillation. And then you normally, the defibrillator will notice this VFib condition. It's essentially the heart is in a chaotic beating pattern, not beating normally. And normally the device will pick up on this VFib and then emit a defibrillation shock to effectively reboot the heart to begin beating in a normal sinus rhythm again. Now, the reason why this was possible was there was a debugging, what I would effectively consider a human debugging command, because anytime a patient gets one of these devices, they go into the electrophysiology lab, they're on the table, they get the implant, but you want to do an end-to-end test to make sure that the device was implanted properly. Well, you can't just wait around for the patient to have some kind of cardiac arrhythmia. So what do? You induce it. And so built into these devices are commands to induce the deadly heart rhythm that it's designed to then restore the patient from. And so the problem here was this command to induce the ventricular fibrillation was not authenticated. And so this sort of end-to-end test demonstrated that lack of authentication and raising awareness to the importance of having stronger security controls on these devices. We, of course, tried to find volunteers to do this, and not being able to find any, we did it on explanted devices that are no longer used by patients. So that was, again, about 15 years ago. Over the last couple decades, sensors have been making their way into pretty much every part of our lives. And so if you want to read, I have a paper on this in CACM from a couple years ago about the risks of trusting the physics of sensors. but you'll find them inside airplanes, smartphones, for how you go to landscape to portrait mode. There's a sensor that helps you do that, accelerometers and gyroscopes. Within automobiles today, the traction control systems depend on MEMS sensors in order to know when to kick in that traction control. Airbags in cars use a series of accelerometers to determine when to do that detonation of the gas charge to release the airbag. You also find, for instance, here at the University of Michigan, we have autonomous vehicles. Here we are, my research group on one of the autonomous buses, no driver, rolling around using sensors in order to navigate. You also find them inside of satellites. And so here we have a picture of a cube satellite that is now replacing things like reaction wheels with MEMS accelerometers and MEMS gyroscopes. These are tiny semiconductors that can help you determine certain things about the inertial properties of a system without having a gigantic wheel inside this tiny satellite. And then, of course, in Washington, D.C., they're always very progressive. And so they actually had here the first underwater autonomous robot here at a shopping mall after it accidentally went down the stairs. Oh, do I see we have a question? I'll let David handle that if that's something to take notice. I see there's a chat.
So I'll ask a question here on behalf.
Okay.
So it comes from Kevin Hoying. I hope I'm saying that correctly. Actually, Kevin, I guess if you want to unmute yourself, you can ask your question directly. Or I'll ask it for him. Okay. So
sure, I'm there, but Kevin knows me. I was just noting
Kevin,
that.
how are you?
Good. How are you, Kevin? I was just noting that the receipt of an induction command through lack of authentication is one method that you'd protect. It would also just be a simple condition just to recognize in the device that induction is never safe if therapies are off. And so the safety analysis also missed that.
Yeah, good point. And in fact, in this now ancient paper, as you're probably aware, we talk about if you're testing a property P, if there's a trigger for it, that effectively the restoring function ought to be available if you want to consider this sort of a safe procedure. So yeah, although I still believe that cryptographic protection, when possible, is a good control, especially when it's in constellation with some of these fail safes.
No argument.
Mm-hmm.
We have an additional question from Jill, I guess a follow-up question from Jillian here.
Yeah, I see there's a question about from Jillian, but does that safety mechanism require anticipating all the safety risks? So this will get into, I have a different talk I could give, but let me just summarize my other talk on threat modeling as in computer security engineering, we have something known as threat modeling. It's sort of the hazard analysis equivalent to computer security. And there are different kinds of threat modeling. And I would say some of the most effective threat modeling is the kind that can actually prevent unknown computer security risks. And the way you do that is through creative security models that are not locked into today's technology, but focus more on properties that you can make reasonable assumptions about toward the future. And so if you want to be able to build, and this is independent of medical devices, if you want to be able to build a system that's going to remain secure for decades rather than just months, I would say it's strongly linked to the degree of the creativity and refutability of the threat model. I don't want to have to look through a list of every CVS score in the world of all buffer overflows. I want to make sure, for instance, that I have end-to-end security by not assuming I trust the network for anything. And that's the way I've been building my systems for the last 20 or 30 years. When I build a cryptographic file system, I make no assumptions except availability about that network. And I want to make sure that an adversary who can control the ordering of packets, duplicate packets, destroy packets on the network, I want to make sure that that powerful adversary, no matter what mechanism they use, cannot interrupt my end-to-end security other than disabling that network connectivity. So, but I'd be glad to give a second talk on that sometime in the future. So let me return to this discussion of sensor security, and I will posit that I feel like computer scientists love abstractions. That's sort of what we do. But abstractions lead you into a false sense of security. And you have to realize that abstractions are not some kind of magic force field. There are exceptions to every rule, even things like bounds checking and C++ coding, right? There's all sorts of bizarre things that can happen if you violate some of the assumptions of the threat model of the underlying system. And intentional interference, whether it be vibration or acoustics or radio or light or heat, it violates a lot of the assumptions of sensor output integrity. And that leads to a problem of sensor spoofing. And so for the rest of this talk, I'm going to be walking through different modalities of sensor spoofing and suggestions I have on how to engineer these problems away so that we don't have to just keep guessing what the adversary is going to do in the next year. So let me illustrate that with an example from one of my recent alums, Dr. Sarah Rampazzi, who's now a professor out at the University of Florida. She was playing with this thermocouple in my lab and noticed that, well, first of all, a thermocouple helps you display temperature. If you want to know what the temperature is in the room, you probably have a thermocouple. A thermocouple uses bimetals, and it produces a small voltage potential that is proportional to the temperature in the room. Compared to a reference temperature. But it's not necessarily temperature. It's actually just interpolating from a voltage potential and guessing what is the temperature in the room from this tiny millivolt peak-to-peak signal. Now, if you happen to have an antenna nearby, as you can see Sarah has here, that antenna can cause potentials to build up, treating the thermocouple as a receiving antenna. And if you zoom into the thermocouple we have here in the lab, you can see it reads negative 1,847 degrees Fahrenheit. And I know you're in Canada, so in Celsius, that's pretty cold as well. In fact, this is negative 770 Kelvin, which is below absolute zero. So we call this the absolute zero-day attack. But my point is, we have systems all around us that depend on sensors, and yet they make these rather large assumptions about threat models of the world. And here's a case where just using an off-the-shelf little radio transmitter, it's even done similar things with a nearby walkie-talkie where you're not even trying to cause the harm, but it just accidentally interferes and causes these false readings. Imagine now if you can have this inside of a security threat model. Now for thermocouples, why does this matter? Well, we put thermocouples all over the place. You ship a vaccine, and you want to make sure that it has a cold chain transport. You will likely be using some kind of thermocouple. If you have embryos stored in a cryogenic chamber, you're likely to have some kind of thermocouple to help with the closed loop feedback to cycle the coolant to keep it at a safe temperature. And so there are definitely safety critical systems that depend upon high integrity outputs of thermocouples. So what's the key research problem here? As you know, the ultimate problem is it's affecting humans from a societal point of view, but the key problem is how do we protect things like medical devices and cyber physical systems from emerging threats that we don't know about from analog sensor integrity problems? And so that's what we're going to talk about. And this is a classic figure that you'll see if you ever take what's called control theory in an electrical engineering, sometimes a computer science curriculum, and you have this loop. And if you're trying to, for instance, keep your airplane stable, you have a closed loop feedback system where your sensors are telling you about the stability of your airplane, and then you constantly change components of your cyber physical system to remain in dynamic stability. And so if you can have an adversary who can control the sensor output using tiny signals, that is sort of the backdoor way in to controlling what the controller tells the system to do. And very often we can emit signals from that sensor to trick the controller into causing the system to become unstable in coherent, incorrect ways. So I'm going to talk about 3 different kinds of modalities, working through the radio world, the acoustic world of sound, and then also light, primarily lasers. I'm not going to talk about ultrasound today, but it has similar properties to audible sound as well. But you might think for a moment, like what medical devices depend on sensors. So I'm not sure if there are any students on the call, but if there's any students on the call, I'd say, hey, tell me what kind of medical devices you think might use a sensor. Feel free to write it in the chat. I'll take a look there. But think about just for a moment, what medical devices out there or other cyber physical systems depend upon sensors for their behavior. While you're thinking, I'll just point out this is a picture I've found from some ancient archives on medical device quackery. Okay, well, I can see we have some folks who are a little afraid to ask, but I'll just say pretty much all modern sophisticated medical devices have some kind of sensor, whether it be for the therapies, excuse me, for the diagnostics themselves, or for some kind of control loop feedback system in order to change how the therapies are working. And oh, this is interesting. Zoom has failed by making my mouse disappear, but I can see its outcome. And David says insulin pump. That is correct. Insulin pumps, for instance, very often will have a glucose sensor connected to it. Typically on the body somewhere, a glucose sensor is taped. And then there's usually some kind of RF link between that sensor and the belt-worn insulin pump. An fMRI machine, would that be considered a sensor? Sure. You know, an fMRI is effectively one giant sensor. It's emitting interesting energy and then looking at that energy as it comes back to do the functional MRI. So sensors are all around us. Let me get back to the presentation here. So one second. My mouse disappeared, so let me reset. Okay, I think we're better now. So let me tell you a little bit about how RF can affect medical devices from a security point of view by asking you the following question. Just think for yourself, you know, which of these two is the correct cardiac signal? Is it the heart rhythm on the left, choice A, or is it the flat line B on the right? And as you're thinking about this, you should be asking yourself, well, wait a minute, it depends. Like, is the patient alive? So the correct answer in the particular use case I'm going to talk about now is B. We're trying to make sure that our pacemaker is able to detect the lack of a normal sinus heart rhythm, or a flat line in this case. And if for some reason the pacemaker detected a normal sinus rhythm, that pacemaker might have actually stopped pacing the patient's heart if it notices a ventricular sense. And so we want to figure out, how do we make sure that medical devices and other cyber physical systems receive correct sensor output so they don't make the wrong binary decision. So in computer security, we've made great headway in things like securing network traffic and using software updates, but the sensor readings, even though people like me have been talking about it for over a decade, it's still, I would say, rather unprotected. It's basically the back door into many modern IoT systems. And so I'm going to talk about a microphone. And it's something that I think most people can relate to, especially now in this day and age of Zoom. But imagine you have a microphone or a lavalier or something clipped to your shirt. There's a wire running from the microphone to some electronics. And that wire has a length, and therefore it has a resonant frequency. And if you can emit RF signals at the resonant frequency of that piece of wire, you're able to actually induce interesting electrical properties on that wire that are then amplified, converted from analog to digital, and delivered to the microprocessor as if it were audio. And so we're going to walk through how this actually works and what you can do with it. But you can imagine most microphones or even pacemakers have a lot of interesting analog circuitry to filter out unwanted signals. And here we're going to do something called a Fourier transform. But if you're not familiar with the concept of Fourier transform, just think of the equalizer on your like a fancy stereo system with the low tones and the high tones. So imagine that your baseband, the signals you want your cyber physical system to get, are rather low frequency. And then you have some interference that's really, really high frequency. Well, it turns out there are these circuits called low pass filters that can just get rid of all the high frequencies. That's pretty trivial to do. The problem is, what happens if signals come in what's known as the baseband? Well, the hardware is not going to be able to filter those out because those are the frequencies that were designed to receive. So in fact, those are sort of the worst case scenario where it will get into the system And the system somewhere in the higher level in the software stack will need to make a decision on whether to accept these signals as real. So let me demonstrate what happens when you don't have a firm grasp of this problem. One of my former postdocs, Dennis Foucault, took apart a little webcam that had a microphone in it and put it on the table here. And then just about a meter away, he placed a software programmable radio, and he's emitting certain tones with amplitude modulation. You can kind of think of it as like an AM radio station. And there's a completely silent room here. And when he played RF signals from a meter away, this is what the microphone heard as it told the Macintosh that it was connected to. So if you could hear that, I believe that was the Weezer song that my postdoc introduced me to. It was clear as day in this silent room. He basically turned this microphone into an unintentional radio demodulator, or AM radio receiver, without the device even knowing that it's become an AM radio receiver, and effectively fooling the sensor by causing the microphone to deliver electrical signals up through the signal conditioning chain to deliver this false audio to the computer. And the computer was none the wiser, simply accepting it as integrity protected and authentic. Why does this happen? I know this is more for sort of the social side of computing and less so on the electrical engineering, so I'll just sort of hand wave this a little bit, but it all has to do with a property called nonlinearity. This is a property that you learn about in sort of first or second year electrical engineering courses. It's basically considered bad. It means you have a crappy component, like an amplifier that's not working so well. And the result of nonlinearity is that you tend to get copies of signals where the signals are accidentally copied by the circuits, but sort of distorted at higher frequencies, all the sums and differences of every frequency. And it turns out you can use this to create a radio demodulator. And I bring up this figure because it turns out, well, although we published this over a decade ago, or about a decade ago, it turns out that this figure is true for many, many different systems, whether it's radio, whether it's lasers, whether it's acoustics. We have nonlinear systems all around us with sensors. And so we actually found this to be a very general problem in sensor systems across many, many different markets. And so I'll just leave it at that for this particular audience. Now, at the same time, pacemakers and defibrillators rely heavily on sensors to do their job, and these devices are safe and effective and do wonderful things to help patients lead more normal and healthy lives. Today, we're going to explore the boundary conditions and the edges of that as it relates to sensors and security. So, for instance, your cardiac rhythm, typically most of what I'll just say is your quote heartbeat in sort of layperson's term, is concentrated in about 10 to 100 hertz. That's where most of your cardiac signals exist. And so you can imagine that a pacemaker or defibrillator could filter out a lot of the other signals. But if adversarial RF comes in within that baseband, it's much harder to filter that out at the electrical components. And so I'm going to show you what happens as a result of RF coming in within the baseband of what you're expecting to see on a pacemaker. So Dennis set up a couple experiments. One, he filled this little bucket with saline solution to approximate the salinity of human tissue. And the other, on the right-hand side, what we've got is a pacemaker taped on a wall with what's known as the electrodes or leads sort of curved on the back there. And those electrodes are basically acting for us as unintentional RF receivers at this point. And what we wanted to know was, well, what are the limits of this? Could it have any appreciable effect on the device's decision-making? And also, how close do you need to be before it becomes clinically relevant? But again, we're going to explore what we used to do on microphones. Now we're going to ask, can we do something similar where we emit RF on a pacemaker and cause its sensing technology to missense effectively some cardiac arrhythmias? So there's sort of two answers to this question. The first answer is yes, you can affect it. The second question is how clinically relevant. It turns out, my personal opinion is that this is not particularly clinically relevant for the average adversary. But let me show you what we're doing here. On the left-hand side, we're emitting a sine wave over radio, but we pulse it every 1 second. And so we thought, oh, if we pulse it every 1 second, that could get misinterpreted as a 60 beats per minute normal sinus heart rhythm. And so sure enough, here we have a screenshot of the physician's pacemaker programmer, this external device that gives you real-time analytics of what the pacemaker sees. And you see this little green VP standing for ventricular pace when it's emitting a small shock to artificially cause the heart to begin beating. But then in line with our 3 pulses of interference, you see this VS, which stands for ventricular sense in purple. That's the pacemaker telling us, hey, wait a minute, we detected that the heart is effectively sort of pacing itself and does not need electrical stimulation, and so it can avoid having to emit a shock, effectively saving a little bit of power. And then when we turn off the interference, the ventricular pacing resumes again. Now, what would happen if this interference was going on constantly? Well, this particular pacemaker as programmed would not be doing any kind of ventricular pacing, and more than likely that would lead this particular patient to faint, no longer having a pulse because of the lack of the artificial pacing. Now, I said as the good news, however, we find for this particular RF at sort of reasonable power, you have to be really, really close to the device to cause any appreciable effect. We're talking on the order of 3 to 8 centimeters. And the reason for this is that a lot of these signals are just readily absorbed by human tissue because we're basically bags of saline solution, and they absorb these particular frequencies quite well. For body-worn devices, I think you may get a different answer, and the jury's still out on what are some of the potential effects for body-worn devices, whether it be an IoT device or a camera or a medical or a health device. I'm not aware of any research on that at present. So that's an example on the RF side. Now I want to go into the side of acoustics. So I had a colleague in Korea who discovered that by emitting sound waves, he could cause drones to drop out of the air. And that was a little strange. And it turns out his sound waves were affecting the gyroscopes on the inside of these devices. And so we tried to replicate that. And in the process of replicating it, we found that we could also not just disable certain inertial sensors, but we could control the output of those inertial sensors. And so let me play a short video. Here we have a Fitbit inside this little Tupperware with acoustic shielding, because it's going to be a very loud ear-piercing sound at around 13 kilohertz. It's like scratching a chalkboard. And that is the resonant frequency of the semiconductor inside the Fitbit's accelerometer. And you're going to see the step count increasing here. You might even be able to hear the whine at about 11.5 kilohertz. 80, 81, 82, 83. As you can see, the step counter is going up because as we're emitting these sound waves, just like with a thermocouple does not measure temperature, it measures voltage potential. An accelerometer doesn't actually measure your motion as you're walking around. It's measuring interesting electrical effects on a semiconductor that are normally a proxy for acceleration. But in this case, because we hit the resonant frequency of the semiconductor material, we're able to trick the accelerometer into delivering effectively false signals into the microprocessor that are misinterpreted as steps. So some of my students thought this could be a fun like ringtone that we could sell online as a funding model for the lab, but we never got around to that. Let me show you a bit more precisely what's going on through a demonstration. So here you're going to see me typing and touching a Samsung smartphone. By the way, probably this video you can download from YouTube, but I wouldn't recommend you play this on a Samsung smartphone. And what you're going to see is I'm going to touch the smartphone to begin to play a malicious YouTube video. It has malicious audio laced into a real music video. And as the sound is being emitted, it's being mechanically coupled from the speakerphone across the circuit board inside of the phone to the accelerometer that's soldered to that same circuit board. And because of that mechanical coupling, the speakerphone becomes a transmitter of the malicious signal that fools the accelerometer into shaking at its resonant frequency, allowing us to deliver chosen outputs of the sensor. And you're going to see on the Mac here, I've got a little Bluetooth link set up, and it's basically an oscilloscope, a time series. It's going to show you the acceleration over time, and it's going to spell English words out. That's our way of proving that we can control the output. So here we go. We're going to play our tone. Okay, so I'm not sure if you could hear that annoying tone or the annoying music video. But that's my son's favorite music video, apparently. He likes to fool his brother into watching it. It's spelling out the word walnut. So I asked my students, hey, I know you've got measurements. How about think of all the English letters that are functions and not relations, and therefore you can actually print it out on the oscilloscope screen. And so they modulated the word walnut using amplitude modulation, just like an AM radio station, onto a acoustic carrier, where that carrier frequency is the known resonant frequency of the semiconductor material. And so you can find this video online if you want to play it yourself. But oh, I see we have a couple questions. Did you just rickroll us? Yes, I did, but it was a real video. And yes, Jesse, I just rickrolled you. Okay, let me continue back to science.
Those are not real questions.
But still good questions. So I use the word resonant frequency in a hand-wavy way. And I want to go back to sort of high school physics and all sorts of fun things. So first of all, what's a MEMS sensor? MEMS stands for microelectrical mechanical system. They've been around for decades. And they've slowly invaded the marketplace such that they're pretty much in every device you own. My smartphone must have at least 3 or 4 different MEMS devices, including a MEMS microphone, a MEMS accelerometer, a MEMS gyroscope. It probably also has a MEMS speaker, but I'm not 100% sure on that. There are also MEMS clocks. For anyone who used to build computers, if they went through a computer science program in like the 80s or 90s, you probably had to build a computer with a crystal clock. No modern smartphone uses that crystal clock anymore because it's kind of big and wonky. Instead, they use a MEMS clock. Well, anyhow, a MEMS clock, if you get a microscope out, it has really, really tiny mechanical components on the inside that are, for instance, maybe shaking. And the shaking around causes changes in the electrical properties of the system. And then you can deduce from these electrical changes things like acceleration, change in rotation, temperature, all sorts of things like that. Now, where it gets interesting is these materials, just like human beings and wine glasses, all have resonant frequencies. And you might recall the old case of an opera singer who can shatter the wine glass by hitting the high note. It's exactly the same concept. If you can hit the note at which these devices resonate, it will have maximum gain and it will shake the most effectively. And so what I've got plotted here, the lead student on this, Tim Triple, he did what's called a frequency sweep, where he would emit tones at pretty much every frequency from the very low tones up to ultrasonic tones. We're talking ultrasonic, we're talking 20, 30 kilohertz. And we would look for weird changes of output from the sensor. And anytime we would see a high standard deviation across all of our trials, we made a pretty good educated guess was we probably hit the resonant frequency at that point. And so these sensors will often have multiple resonant frequencies, but there's usually one that's extremely profound. And that's where you can get the maximum amplitude delivery of the malicious signal. And again, since we're more of a human social computing today, I'm not going to get into the signal processing so much. I'll have a few slides on it right now, but I'll just say you look for sort of the maximum impact on the resonant frequency, which you can detect by profiling these devices ahead of time. And it's going to lead to a couple bizarre cases of the sensor producing either a fluctuating output or a constant output under control of the adversary. So I'm deciding whether to go deep into the physics here. I think I'll skip the physics now just because this is not a physics crowd, other than to say the root cause has to do with some of the choices designers make in how they're filtering and amplifying these tiny little signals inside of the computer chips. And because of that, And because of the nonlinearity property, among other things, you can modulate whatever signal you'd like to come out of that particular sensor by modulating it on top of that resonant frequency. You treat it like a radio station, basically. But here we have an acoustic carrier rather than an RF carrier. The fix is really interesting, in my opinion. So normally in the United States, we have the Department of Homeland Security and CISA that will issue vulnerability reports. And usually at the end of the vulnerability report, it tells consumers, hey, apply this software patch and you'll be good. This was the first case I've ever seen where the end of the report says, drill your holes differently in the circuit boards and you'll be okay. And the reason for that is Analog Devices, who helped sponsor some of the research, pointed out that if the mounting points, for instance, in your phone are very far apart, then your circuit board begins to act as a drum. And this drum is going to be much more flexible the further away these mounting points are, causing this sort of secondary acceleration from sound pressure generating board vibration. So they said, well, if you drill your holes closer, you're going to make that much more rigid, driving those resonant frequencies into the ultrasonic range, which is a little bit harder for an adversary to do. And they also recommended doing something called trenching, doing printed circuit board trenches between emitters and sensors such that an adversary who can deliver tones from a speakerphone is not as easily able to do mechanical coupling to, for instance, a microphone or an accelerometer or a gyroscope. And so this is what is being advised to the industry today to mitigate these kinds of risks of sensor tampering, sensor spoofing. Oh, and I see we have a question. This is also the first time I saw sine waves inside of a CERT report, but let me get to this question here. Whoops, just a moment.
I was just asking if the PCB designers now have to be aware of the threat model of the overall device. This seems not scalable, like just from a manufacturing standpoint. Not manufacturing, but device design standpoint, like everybody now has to be aware of all the security threat models on the device.
Yeah, so I would say it's all about volume. So the more I would say that a device has reached sort of ubiquity in a market, the more you're gonna have to care about this. If only 10 people are using it, in my opinion, it's probably not going to be a very tempting target. Then again, if you heard about the NPR radio stations last week, where certain NPR radio stations, National Public Radio near Seattle, had accidentally emitted a particular packet on digital radio that caused, I believe, Mazda entertainment systems to fail permanently. And nobody understood why all these Mazdas around the Seattle area were failing. And it turns out there was an encoding of a particular image for the radio station that triggered a latent decoding flaw in the radio software. So where am I going with this? I do think people need to worry about it if they're going to be designing consumer products, because some of these attacks are actually not that difficult to pull off. And now that we're having things like LED lights all over the place, where there's a microprocessor inside that light bulb that has software or firmware in it that can be updated, I know just from experience that it's only a matter of time before an adversary can take control of these light bulbs, change the software ever so slightly to change the flickering of the light to emit RF tones, RF, at the resonant frequency of something interesting, basically making any distance-based argument for security moot, because we have these transmitters all around us. So the question is going to be, as these products become more and more ubiquitous, how do we make sure that they remain trustworthy, even if an adversary is just a few feet away from you with a transmitter? But definitely smartphones. If you're a smartphone manufacturer or an IoT manufacturer where you're expecting more than 1 million units of volume, these are problems you're going to have to worry about. So the good news is there are some solutions that don't require hardware modification, and they don't solve all the problems, but I'll just illustrate it with one example. One is called randomized sampling. So anyone who does computer engineering will know about something called interrupt handlers and polling. And there are many systems that will poll a sensor saying, for instance, what's your acceleration? What's your acceleration? What's your acceleration? And then they use that output, for instance, to determine, hey, did I take a step on my Fitbit? Well, there's a really simple change you can make, and that is introducing a randomized delay at each sampling interval. And as long as the signal you're trying to actually measure is fairly smooth and not changing dramatically within a single cycle of the sampling, doing a phase shift should have no appreciable effect on the actual outcome of the desired sensing, like did I take a step, but it's going to totally mess up the adversary in certain cases where the adversary is trying to exploit periodicity in order to get their exploit into your system. Again, this doesn't solve everything, but it does solve certain cases where a periodic adversary is able to exploit a sensor through these unintentional demodulators. Okay, well, let me move forward to the last modality of light, so we have time for questions. And that's some work we've done on lasers and even flashlights, where I had a colleague from Japan, and he showed me how he was able to use a little laser pointer, and if he shined it on a microphone, you could hear it. And we found this very interesting. It turns out actually flashlights do this as well. If you take a LED flashlight and turn it on and off really, really fast, certain MEMS microphones will hear sound, which is just very bizarre. And so it was a very interesting physics problem. We published some of the early work at Security a couple years ago. But I want to talk about just some of the social implications to voice assistants. So Daniel Genkin pointed out, oh, well, wait a minute, voice assistants use microphones. Does this mean you can fool a voice assistant into doing things from a far distance? And so here in the picture, this is an actual picture. This is not doctored in any way. We are shining a laser from the bell tower across from our computer science building through a plate glass window, hitting the microphone port of a Google Home and causing that Google Home to hear a false voice that's going to make a command happen. And so the reason for this is really complicated, having to do with some of the physics of semiconductors and thermal pistons and how certain materials absorb light and turn it into sort of interesting electrical side effects. But I'm going to focus more on the outcomes today rather than the causality. So let me go through this experiment. By the way, if you're a computer scientist, it's pretty hard to convince your university to let you shoot lasers around, even low power lasers. But we took our low power laser and then we hooked it up to a telescope. So you can see this little telescope on the right-hand side. And instead of using it as a telescope, we used it as a collimator in order to extend and control the beam forming of our laser so that it remains coherent as it hits an object that's not actually on the white wall there, but twice as far away on the brick wall, about 300 yards past that, or 300 meters or so. So we are going to be emitting light where we have modulated that light on top of a carrier, again, to cause that microphone to pick up false sounds. So I have a little video here that explains how this works. I believe this is the one with the bell tower. So let me play that.
Okay, opening.
So that was an example of a cyber physical system, just a voice controlled assistant, but because it contained a MEMS microphone, we knew we could control what that MEMS microphone was telling the microprocessor by shining a light at it. And again, this works with laser pointers, literally the laser pointers that you use in the classroom. By flashing it on and off very quickly, we use a little homemade circuit to flash it on and off without having to use our finger. Get a lot of probably tendonitis that way. But it also works on flashlights. And so we were really surprised when we took a consumer flashlight and turned it on and off at a rate proportional to audio that we wanted to deliver, and that worked as well. And it stymied many of the semiconductor manufacturers. They said this shouldn't be possible. But sort of that's what my lab specializes in. We do what most people think would be impossible. I'll show part of a video here explain what's going on, a little bit of the physics, and then I think I'll open it up to the last minute for questions since David, I think how are we doing on time?
Actually, I think
4 o'clock.
there's some room for questions at the end, so I guess we can eat a bit into that since we've been asking questions.
Oh, okay.
Take your time. Yeah, just go ahead.
Okay, I'll play part of this video so you get an idea of what was going on.
In May 2019, researchers from Japan and the University of Michigan discovered light commands, a vulnerability in most microphones that allow attackers to remotely inject commands into voice assistants such as Google Assistant, Alexa, and Siri. So, how do light commands work, and how can we defend against them? Voice assistants operate on commands spoken by the user, such as, Alexa, what's the weather? Or, okay, Google, unlock the front door. While the security of voice assistants is a common concern, assistant-enabled devices are typically kept indoors, where access is restricted to only legitimate users. So why are light commands so dangerous? To understand light commands, let's take a look at how microphones work. Microphones convert sound into electrical signals. Inside each microphone, there is a small plate called the diaphragm. When sound hits the diaphragm, it moves, resulting in electrical signals. An attacker may try to move the diaphragm by yelling from outside. However, as solid objects block sound, the command will probably be ignored, as well as noticed by nearby neighbors. Light commands, on the other hand, exploit different tactics. Instead of sound, an attacker can encode commands via the intensity of a laser light beam. By shining a laser light through the window at the microphone, an attacker can remotely cause the diaphragm to move. This results in electrical signals representing the attacker's commands, which are then acted upon by Alexa, Google Assistant, or Siri. Making things worse, light commands can be mounted easily and cheaply, even using regular laser pointers. This can even be done from far away, for example, between 2 buildings. Even more worrying, once an attacker has gained control over a voice assistant inside a phone, tablet, or smart speaker, they can use it to break other systems. For example, the attacker can control smart home switches, make online purchases, open smart garage doors, remotely unlock and start certain vehicles, or open smart locks by brute forcing the user's PIN number. So how can we defend against light commands? Well, the basic vulnerability cannot be addressed without expensive microphone redesign. We are collaborating with Amazon, Google, Apple, as well as other vendors on defensive measures. If you would like to know more, check us out at lightcommands.com.
All right, so that sort of gives you a high-level picture without getting into sort of measurements and graphs on what's going on. We've walked through sort of 3 examples today, beginning with radio, doing a little bit of acoustic with sound, and now with light. And you can start to see the theme. These sensors are being fooled by the physics because sensors are just proxy for reality, and they don't actually measure the measurand that you intended. So if you've got a cyber physical system and you defend on sensors, what can you do? I would say, well, you can still use these devices, but you need to verify those outputs somehow. And this is where I think we have some really interesting research challenges to solve over the next 10 years. And I've sort of categorized these into three different areas. One is from an educational standpoint. I think we as educators in the universities need to do a better job demystifying the analog sensor attack surface. So we've got really good textbooks on cryptography and security engineering, but we need to see, I think, some emphasis on how to test security to failure rather than like, I don't know what's going on. And so we want to be able to push these devices to edge to know their tolerance level. You know, I basically want to come up with the equivalent to tensile strength testing for computer security, and that's not just going to be penetration testing. But I also think in the classroom, we need to spend more time on unwrapping a lot of the classic abstractions that we teach students, whether it be in electrical engineering, mechanical engineering, computer science, material science. We make all these assumptions to make things appear simple, and that's exactly what the adversary is going to exploit. The adversary likes to exploit the undefined behavior at the interface of different things. And so that's why I think unwrapping is really important so that students understand not just how things work under normal conditions, but how can they work under bizarre boundary conditions. The second category has to do with moving away from the traditional commercial world of buy this product, go to sleep. We need to move away from just throwing things at the wall and seeing what works to a more measurable science for computer security. So in this particular case of sensors, I think we can do a better job physically de-risking a lot of this intentional interference with more deliberate hardware specifications and design. So for instance, if the designers were more aware of their own resonant frequencies, they could build in controls to try to eliminate that. I can say during some of our experiments and briefings of vendors, one vendor told us, oh, well, that explains why whenever we'd honk the horn, our airbag sensors would go off. And they said, well, we just put padding around it and hope that would fix it. And so we also see that some cases that were not security incidents, but were more about reliability and safety, were also being tickled by some of these acoustic problems. So being more deliberate with hardware specification, I think, can help. But I personally think sort of the most effective approach here from a preventative rather than retroactive, how do we fix this, is rethinking integrated circuits and these hardware software application programming interfaces. So I would like to see these sensors no longer just saying something like, hey, here's my audio, or here's the acceleration, have a nice day. I would like that sensor to give me a second line of information that says, here are some hints on why I think you should trust that this sensor has integrity. So I'd like the hardware to convey these hints of trustworthiness so that the software stack can have a much more end-to-end, more reasonable guarantee of trustworthiness. So this could take the form of many different things. It could be a single sensor that has multiple outputs, or it could be the integration of multiple sensors using different modalities. For instance, a Hall effect sensor combined with a different sensor for looking for magnetic strength, sending these 2 signals or 3 signals to a microprocessor. And if you see divergence in the signals, you have a reasonable understanding that something's not quite right. And you probably ought to red flag that sensor as well, use it, but we shouldn't trust that that input is true. The other thing that I find is just, these computers have always been vulnerable to these types of threats since the dawn of time. The only reason we're talking about it now, in my opinion, is that the degree of connectedness and dependence has just skyrocketed. And we're also beginning to remove the human in the loop to many of these automated systems, and that creates automated consequences. So if you have an error-prone process and then you automate it, you just get faster errors. And this has increased risks to the properties of availability and integrity. Availability meaning, whether that device is available to do what it's designed to do, in integrity, you might not be able to trust what the output of a sensor is if it doesn't have high integrity. But finally, maybe it's just not a good idea to put a computer in everything unless there's a really good reason in looking at the balance of risk benefit. So for related work, there's a lot of great papers. I've got some of the technical papers listed here. You can do a screenshot, I suppose, if you want. There's also some high-level documents. The Computing Research Association issued a grand challenges for embedded security research. That's more high level about some of the big problems to solve. I would say, this is a really important thing for if you're a student, for instance, to be working on now. I think it's a great thing for a thesis topic because there's a lot of interesting problems to solve. And it's important now because consumers really need to have confidence in the security and privacy of these technologies if we want to have any hope they're going to trust in innovative medical devices and other emergent technology that's going to change how consumers live and behave. Let me end with a couple sort of advertisements. So I have this vision for education where we're going to be translating computer security education into other domains, sort of like computer security plus, where we can combine it, for instance, with biomedical engineering, because I think a lot of the concepts from security engineering are very approachable if you are able to deliver it in a way such that you don't need to have the computer science background. For instance, threat modeling. I think, is an art and practice that is very approachable, whether or not you already have computer security training under your belt. And so that's something I would like to see biomedical engineering students learning if they expect to go into the product development world. But we have a seminar series at UCSF Stanford where you can hear a lot about this, and all the YouTube videos are up there at that URL there below. Other sort of inspiration, especially for the students on the line, I think there are a lot of really cool grand challenges for what's become known as operational technology, or OT security. This is computer security for everything that's not IT. So IT is very data centric, but don't forget all the cyber physical systems, whether it be the factory floors or the airplanes or the medical devices or the satellites, things that help people and are deeply ingrained in how society functions. There are a lot of interesting research challenges, and number 4 I like to highlight again is just, I think there's so much opportunity for integrating the research and education from computing and computer security into these different fields, so that we no longer think of computer security as buying a product and more about design patterns. So I'll just say thanks, thank my associate editors here, and end with, you know, I believe microprocessors should not just blindly trust sensor outputs. I think there needs to be a way for the end-to-end software to verify it. And I think we can do a better job at protecting these emerging IoT devices by using software that leverages the fundamental physics. For instance, detecting the resonant frequency is something that software can utilize in order to be more defensive. And finally, I think if we shift our thinking to systems engineering, by focusing on trustworthy systems rather than secure components, we'll be in a safer place. And the reason for that is secure components, I would say, are sort of shades of gray. There is no such thing as a secure component. All secure components can be broken eventually with enough force. And so the real question is, how do we build a system that's going to remain secure according to its definition of security, even if some of the components fail? And that's where I think we're going to have the most potential for success. So I'll just end there and hand it back to David, and be glad to take any questions on any directions here. So thanks for listening. Oops, and David, I think you're muted.
Sorry, there's a mute on the headphone. Okay, yeah.
Now.
Yeah, so let me just say that again. So let's everybody thank Kevin, and I guess we can take questions either on the chat or just simply raise your hand and I will call on people. Okay, so let's start with Jillian, and then Matt, and then Lisa.
Great. Thanks, Kevin. That was terrific. And you, of course, got my brain working for the Wordle tonight. Thank you for that. I'm trying to, what should that last line be? I've got 4 letters in somewhere. So my area of expertise is in law and economics. So I think about the environment around this, right? And as you know, the engineering issues here that you've identified. So I guess I wanted to ask you, and this is something that David and I have been talking about over the last couple of years, and I just don't know very much about it. And maybe you have to put your FDA hat on, at least to not to represent views from the FDA, but how do we think, like, what's the regulatory environment around this, right? I mean, like, what do we have in place? What you were sort of thinking, you know, presenting this as, okay, Apple and Google and Samsung and so on should be thinking about this. So what's the regulatory environment that's incentivizing them to do that? And then on the other side, if I'm thinking about threat modeling, I'm thinking about, okay, how do I think about the other tools that we have available to, you know, to deter the threat and evaluate the size of the risk? Anyway, so maybe if you wouldn't mind just, you know, telling me a little bit from your perspective what that regulatory environment looks like.
Okay, well, maybe we'll begin with the first one and then you can re-ask as I'm thinking about the first. So you're basically asking, like, what's the regulatory environment for the Internet of Things or IoT devices? And the joke we have in this space is that the S stands for security and IoT. You know, that's the reason why they're so insecure. And I mean, if you have to look at the different marketplaces, you get the most highly regulated ones like medical devices and avionics are probably two of the most highly regulated. I'd put the nuclear enterprise up there as well. You're going to see a lot more proactivity from government regulation. Now, if you look at the opposite side of the spectrum, what would you think would be there? Well, I would put consumer product IoT devices. There's some regulation. So in the United States, we have the Federal Trade Commission and we have the FCC, the Federal Communications Commission. So FTC looks at sort of consumer issues and FCC looks at things like radio interference, things of that nature. FTC is very court-based, litigation-based. It's not pre-market as far as I know. Whereas in regulatory authorities for medical devices, avionics, that's pre-market. Before a device reaches the market, there are certain rules and regulations that a manufacturer would have to follow. So I think the challenge you're getting to is what the security economics community calls the externality of computer security. Computer security is a classic market externality. The person who can most benefit from added security has the least ability to influence that. And the manufacturer who has the most engineering ability to improve security has the least incentive to do so. I personally think we need to do some more studies on this, but I know of anecdotes where a company will say, well, no consumers don't ask us for this security. They're not willing to pay for it. So why would a venture capital based society invest a dime in security if it doesn't raise revenue? So it's a completely rational behavior, and so when do you need regulation? When there's a market failure. So I would not be surprised if we see more regulations in this space, especially as they go from things, simple things like a light bulb to automobiles. Automobiles is where you start to get into kinetic effects like autonomous vehicles, autonomous driving, any place where you see a human in the loop, but you're noticing the market begin to say, but we're going to remove that human. That is where I predict there's going to be a catastrophe, some deaths, and that's probably when we're going to see action in terms of regulation. Right. But for consumer devices, my money is on more post-market. If a company violates something, they're likely to enter litigation or be brought to court by a government regulator, probably.
Okay, great. And I'll hold my second question and come back because I want to make sure other people get a chance to ask questions. So thanks. Yeah.
Matt, go ahead.
Great talk. It was super fascinating. Thinking about this, I guess I have two questions that are both sort of relate to this point that you made about maybe we shouldn't be putting computers in everything. I mean, one response to this issue, of course, is adding computers to everything. I do a fair amount of electronics work, and I'm always making choices between analog sensors and digital sensors that basically do the same thing, but provide a digital signal that I use instead. And some of those digital sensors include what could be sort of rudimentary security aspects. I mean, what do you think of that as a potential solution, or how are the sort of movement? And I see that as actually a sort of a movement in the industry towards the increase of those kinds of the sensor interactions. How is that addressing, or a form of addressing the security issues that you just described? And I guess the second part of the question, which again goes back to this question of computers in the loop rather than humans, is how does these newer systems of sort of edge AI open up new possibilities for security issues and problems to emerge? So I'm trying to pull back AI into this.
So many interesting dimensions there. So on the first question, are you saying, so I sort of heard two proposed approaches. One was just put sensors or put computers in everything. And then the other approach I think I heard was, well, replace analog with digital. Is that, am I?
Well, I mean, when you replace an analog sensor with a digital equivalent, basically there's a computer being added to that sensor, right? If I take a temperature sensor, I can choose an analog temperature sensor, or I can choose an I2C
type of temperature sensor. And ostensibly it's running a little microcontroller inside of there that's providing in some form of interface to the analog sensor. And oftentimes that interface that is provided to me as the developer includes some rudimentary security features. So, and probably wouldn't be sort of as subject to the same type of attacks.
Well, I mean, the sort of humorous person in me would say, like, it'd be like digitizing a weather rock,
Right.
Garbage in, garbage out. I can see some value in that, but let me come at it from a first principles point of view and ask the question, how does that fit into systems thinking? And Ken points out the world is analog, but how does that come from a systems thinking point of view? So if it's a component you're using, but you still take a systems engineering approach and say, I don't trust that component, I'm going to have a way to verify it, that might be reasonable. But the root of the problem is you can never get completely away from analog. We're not cyborgs, analog cyborgs. We still have analog components. So even inside those digital systems, there's a transduction going on. That's the word in physics, to transduce from the analog to the digital. Packaging it up in a black box, to me, doesn't explain why it's secure. It's more that it's created in an abstraction. So I would just ask the question, tell me about how you do that transduction, and let's, frequency sweep the thing, because maybe it's still allowing me to inject false sounds into a microphone that's producing digital output instead of analog.
Yeah.
So your second question on AI, I think, is really fascinating. And I like to categorize AI into sort of two different buckets. One is static AI or machine learning, and the other is learning, like constantly learning. But also, let me preface this with one of my colleagues, David Evans at Virginia, has this really cute way of describing machine learning from a computer security point of view. He says, look, machine learning is what you do when you don't know how to model your problem. But as soon as you know how to model your problem, and this is my interpretation, you're probably going to choose to implement an algorithm.
Yeah.
But until you really know how to fix it, yeah, use machine learning, because it kind of creates models on the fly for you implicitly. So then there's two different kinds. There's imagine using an AI or an ML algorithm that you've trained ahead of time, and then the training set is static. There, from a safety perspective, you're able to make much stronger conclusions, depending upon whether it's sort of Turing complete. You might be able to enumerate every possible outcome to have better understanding of what are the safety implications. But learning AI or ML, where it's constantly retraining itself, that's a completely different beast. And certainly we have research in my lab where we show that if an adversary is allowed to be part of that input for learning, you can really change the behavior of these things. The most classic example is Microsoft Tay, which I'm imagining many of you have heard about, where within one day, it became the most racist, misogynistic bot on Twitter by learning from all these other people tweeting. So either it succeeded wildly, because maybe Twitter's just deeply misogynistic and racist, but that's what happens when you have a learning system with few controls. And so I think there's a lot of research to do to figure out, okay, how can we move toward this non-static world and still have safety? I don't know what the answer is to that, but my guess would be it's going to mean sort of pulling back on the throttle a bit.
Thank you.
Thank you. Lisa?
Yeah, thank you, Kevin. That was so interesting. So I'm not a tech person, I'm a lawyer. So I'm going to ask you another question about kind of the regulatory environment, following up on Jillian. And like the example of medical devices is interesting, but in some ways kind of easy, at least from a high level in terms of regulation, because we have these regimes of approvals and licensing for medical devices, and it becomes trickier when you think about consumer devices more generally, because it's not a model that scales very well and might not be appropriate in those contexts. So I was trying to think about other kinds of types of tools that we might have in the toolkit to think about increasing security of devices. One would be sort of around standards. And I kind of wondered what you thought about that, is it possible to create kind of security standards? Would it have problems? Some of the problems, again, I'm not a technical person, but just trying to think kind of abstractly about this, might be that we can't, they're just not agile enough in a space that's kind of evolving quickly. Some of what you were saying seemed to suggest that we're not thinking about kind of security in this area well anyway, so we're a long way away from being in a place where we could create standards. I was intrigued by your statement towards the end about we need to be thinking about these as trustworthy systems rather than these secure components. And would that cause problems with kind of the way we traditionally think about standards for things, which seem much more specific? So, and the standards kind of plays into also that even if you have these models where it's based on sort of litigation, we still need to figure out kind of what the kind of, maybe not specific standards in that kind of technical sense of standards, but, did you meet the duty of care that you had in some way to the consumer? So there's still a kind of objective component there to thinking about whether people were kind of behaving in the way they should have. How far are we from a world like that? And is that a kind of a place that might be promising, or a total like non-starter?
Well, I think in the highly regulated world, I have more certainty that we're going to be improving with appropriate balance of safety and innovation and such. In the less regulated spaces of your IoT devices, I think I don't know, I'd give it 50-50. I think standards do play an important role. And I would disagree slightly in that you can have a standard address sort of system engineering, system aspects. Of course, there are a lot of standards that are component focused. So there's tons of standards on here's a cryptographic algorithm. But even if you have the most secure cryptographic algorithm, it doesn't matter a bit if you use it improperly in a system. So I'll hear companies say things like, well, we use military strength encryption. And I'll say, I don't care, because that doesn't matter. It really matters how you use it. And David mentions common criteria, and there have actually been some follow-ons that common criteria is more of an ancestor to some more modern ones today. But in the United States, the Department of Defense cares a lot about system level security for various things. And so they like to focus on systems. I think, but the more we can get away from component-based thinking, I do think we'll be in a better place, because if you think only about components, you're always going to be sort of one step behind today's technology. But if you think about systems, it's a little more forward-thinking, and you don't have to say what system. Is it a voice-controlled system? Is it a driverless vehicle? Well, if you just say we have these cyber physical systems and here are some of the properties, it can lead. It's not going to solve your problem, but I think it's going to help coalesce the thinking to back to basics. And one thing I learned from the medical device community's activities is there are certain elements I think that can apply to any marketplace. Threat modeling. Threat modeling is the bread and butter of any kind of security engineering. And I'd really like to see security engineering textbooks start off with a lot more emphasis on threat modeling, rather than jumping to mechanism or, hey, here's the standard I use on the inside. Because if you don't know what threats you're trying to defend against, you really can't start building a security system, because you don't have a set of requirements yet. And so how do you build up those set of requirements? Well, you do threat modeling, talking about characterizing the adversary, characterizing what is the game? What do you define as success if you're able to successfully defend your system? There's a lot of subtlety in coming up with this. And threat modeling itself is kind of like strategic planning. You don't necessarily follow your plan, but it sure makes you think hard about the problem. So I think that needs to be an essential element of any successful marketplace. The other thing that the medical device community borrowed from the software engineering community is something called the security development life cycle. So in the medical world, we often call it the joint security plan. But a lot of the software companies came up with this security development lifecycle, and it sort of combines a lot of the early pre-market engineering that goes into how do you make your software and make it in a way that you can verify it to meet certain security measures. But it also talks about sort of post-market, what happens when there's an incident out in the wild or a new vulnerability you couldn't predict, how do you handle it? And it doesn't, again, it's not bulletproof, but it helps set the mindset so you have the chance to succeed. So for instance, what's your incident response plan? If a security person comes to your door with a vulnerability report, how do you respond? All these things I think are really important. So if the IoT space did two things, somehow reward threat modeling and somehow reward if you have a very coherent security development lifecycle plan, I think that would do wonders because it would make a lot of other decisions easier. Like, should we have a website where researchers can submit security reports without fear of retaliation immediately? I think that would go pretty far at making the system more secure for the consumers. Let's see. All right.
Sorry, was there a question from Ken? One more? I
Well,
saw his hand
if
up,
we
but
have
it
time,
just
yeah, I
disappeared.
put it down because I thought we were at the time.
Yeah,
but-
we're at time, but I guess there is supposed to be a 30-minute like session afterwards for some people, and I guess if more people want to stick around, I think it would be fine, right, Jacqueline? Like, yeah. So we actually have till 5, but I guess officially the session ends at 4:30.
Okay.
Well, I'll just slip in a geek question for Kevin based on this whole analog digital world. As Kevin and I know each other, I came from the aviation space before getting into medical. And in ultra safety critical systems, critical parameters of the world were typically measured by multiple different technologies. So, nuclear power plant, they won't necessarily use one type of sensor in order to measure the real world. And so you could do cross-checking and fault tolerance to try to detect it. You're interested in your thoughts about that kind of capability and how it might apply to sensor security and from a security perspective.
Yeah, and I think these are all great ideas that used to be confined to the ultra safety critical worlds, but I think that there's also the ultra deployed world. So IoT devices where you have billions of devices, I would argue that collectively they probably have similar sort of safety needs as avionics or a nuclear power plant, even though there are fewer of them, just because of the sheer magnitude of how it affects society. So the idea of using multiple sensors or multiple modalities, that's one I espouse for sure. It has obvious cost issues. So in a consumer electronics world, it's a little bit harder to say, why don't you just double the number of sensors on the inside? But it's great when you can find sweet spots to, for instance, co-op existing sensors. But if you go to an automobile manufacturer and you say, how about just add this 10-cent part? You're probably going to be laughed out of the room. So it's all about identifying, I would say, being able to use what you already have more intelligently. But the higher price the device, I think the more hope we might have.
So when you talk about an automobile and a 10-cent part, I'm still a believer that in order to get autonomous vehicles, if they don't think about triple modular redundancy for safety, we're going to have those disasters that you're referring to, and that's a lot more than 10 cents.
Yeah. But take voice assistants and IoT devices, security cameras, IoT security cameras. We're talking high volume, low cost. That's one where we've already seen incidents of security cameras being compromised. Here's a classic case where the old piece of tape over the lens is an aftermarket enhancement. It's a classic externality. Either we'll need regulation to compensate for that imbalance, for that externality, or consumers will have to take it into their own hands to do sort of aftermarket modification. But of course, aftermarket is always harder because that's like oh, I didn't design for that. How can I change it to do something else? It's always harder to make a system more secure after the fact. And it's always going to be a more cost-effective total to the universe if you do it with well-thought threat models. Oh,
Any more questions?
Okay.
Oh, sorry, go ahead, Kevin.
I think we had a second question earlier, but I think your colleague had to drop off, maybe.
I didn't see it. There was Avery, who's still here, posted in the chat. I wasn't sure if it was a question. Avery, was that a question or just a comment? Okay.
Oh, let me read this. Oh, yeah, more of a comment. Yeah, originally translated from Russian. Mm-hmm.
Well, I didn't know the history of that either. Okay, I guess if there aren't any more questions, we'll thank Kevin again. And I wasn't too sure whether to bring this up, but maybe you're okay with it. But if you want to get more of Kevin, it turns out he also moonlights as a stand-up comedian. So just look around on YouTube and there'll be some interesting videos, more entertainment for you if you didn't get enough of him here. So and let's all thank Kevin again for a very interesting and stimulating talk. And yeah, and as I said, we're sticking around till 5. So if people want to stick around, I think they're welcome to.
Sure, stick around for anyone who wants to chit chat.